With this video, I want to just clear up a few things that may have given you trouble in the 7.2.3 reading on pivoting. First, let me just make sure you understand the basic idea of pivoting, which is what they're kind of implementing in the MATLAB code that you see on page 143. Alright, so again, kind of sticking with the theme of the week, I'm going to start with just kind of a simple example, and then hopefully this will help you understand that what's happening in the code and in what they're talking about in the book is just a more generalized version of this concept. Alright, so in linear algebra, you learned that you can do these row operations. One of them is scaling a row. You can replace a row with itself and a multiple of another row. Or you can switch the order of rows. Any of those are allowed in the process of solving a system of equations. When we did the Gaussian elimination video, the main operation that they're taking advantage of there is that idea of taking some row and adding or subtracting from a multiple of another row. And that's your main tool for Gaussian elimination. Or using MATLAB code, if I wanted to do the second row minus some multiple of the first row, I would have A2 colon minus mult times A1 colon. So again, this would be the entire second row minus your multiple of the entire first row. Now, what this would look like, now in this case, the goal right now is to use this A11 position to eliminate the entries below it, right? So we'll use that 2 up in the top corner to eliminate the ones below it. And so starting, if you're going through that for loop, the very first thing you're going to do is you're going to wipe out that 4. And so in this case, mult would be 4 divided by 2, which is 2. So then I'm doing essentially row 2, which is 4, 2, 7, minus mult, which in this case is 2, 2 times row 1, which is 2, 1, 3. And that gives you your new second row. Alright, so the first row we're not touching yet, 2, 1, 3. The third row we're not touching that one at this point, 3, 4, 5. But then this operation here gives you your new second row. Alright, so our new second row, if you do the math here, would come out to be 0, 0, 1. Okay, now to continue Gaussian elimination, as you run through that initial for loop, you're taking this 2 and eliminating all the elements below it. So we've turned this 4 into a 0, and now we're going to turn this 3 into a 0. So now we need a new mult. So in this case, this next time through the loop, mult will be 3 divided by 2. So then we're going to do row 3 minus 3 halves, row 1. And when you do that, that gives you a new third row. The first, in this case, the first and second rows are remaining untouched. And your new third row, if you do this operation, you should end up with 0, 5 halves, and 1 half. Alright, now everything so far is just basic Gaussian elimination. We used this 2 to eliminate everything below it, and now we have a 2 with zeros below it. In the Gaussian elimination code that you saw earlier, after it's run through this initial process in Gaussian elimination, the other for loop will take you to the next column, and in the next column, now you have a new key element that you're going to focus on, and you want to eliminate what's below it. In this case, though, our mult will be undefined. So in this case, our new multiplier will be 5/2 divided by 0 if we just strictly stick to the code that we saw earlier in the book, which is undefined. So whenever this happens, you have to adjust in some way, and the approach that we take in this section is what's called pivoting, which again, this is basically the same thing. This is the same thing as what you saw in linear algebra, where you said you're allowed to switch the order of the rows. So when we say to pivot, we mean switch this row that has a 0 in this kind of key position with one of the rows below it. Now in this case there's only one row below it, so I don't have any choice but to switch with the one directly below. And then I can continue running my Gaussian elimination code. So now I'm dealing with the matrix 2, 1, 2, 0, 5/2, 1/2, 0, 0, 1. And actually it turns out that at this point, our Gaussian elimination code is going to finish because we have this upper triangular matrix, and now we can just work on back substitution. So in this case, when we pivot, by default, the entry below that 5/2 is already 0, and now we have this upper triangular matrix, and we can easily finish solving the system. All right, now in a larger matrix, you'll have to choose which row you'll want to pivot with. And that's going to be something that they discuss in the book. You'll want to read carefully about it. On page 142, they're going to explain the importance of what we call partial pivoting. Partial pivoting, when you have multiple rows to choose from, here we didn't. We just had one possibility for switching places. We switched the second and third row. But when you have a larger matrix, there's lots of rows to choose from when you do this pivoting step. The idea is to choose the row that has the largest entry in absolute value. All right, so you'll want to read page 142 carefully, because they explain there the importance of partial pivoting, choosing the row that has the largest value. And this will actually be directly related to what you read on page 142, will be directly related to one of your homework questions. Okay, so you'll want to read that carefully and let me know if you have questions. The next thing I'll talk about is at the end of this reading section, there's a theorem that talks about permutation matrices. So I'll talk about that briefly on the next slide. Okay, so when you get to theorem 721 at the end of your reading, I want to make sure you understand what they mean by a permutation matrix. A permutation matrix is basically something that does the pivoting for us. All right, so it'll take a matrix and switch rows for us. What permutation matrices look like, their description in the book is a little bit confusing. So I wanted to make sure it's clear. A permutation matrix, every single row will have a single 1 somewhere in it, and then zeros everywhere else. And then you can say the same thing for every column. Every column has a 1 showing up in it, and then zeros everywhere else. All right, so there's one permutation matrix that you're already fairly familiar with. Let me write this down. So let me put a 1 in the first row, and zeros everywhere else. I'll put a 1 in the second row and zeros everywhere else. A 1 in the third row and zeros everywhere else. And notice also each column has a 1 in it and zeros everywhere else. Now this permutation matrix that I just wrote down, you should recognize as being the identity matrix, the 3x3 identity matrix. And we know what happens if we multiply this permutation matrix by A. So in this case, P times A would just give me back my matrix A without any change. But this is just one example of a permutation matrix. There's others that we could write down. So let's say, for example, let's switch these first two rows in this permutation matrix. So now I have 0, 1, 0, 1, 0, 0, 0, 0, 1 are the entries in this permutation matrix. And notice again, this is still considered a permutation matrix because every row has a 1 in it and then zeros, and every column has a 1 in it and then zeros everywhere else. Alright, now you can try this on your own real quick. If you do P times A in this case, where A is the matrix up at the top, P times A, do that product and see what happens. I'll give you a second to do that. Alright, so when you do this, you'll notice that as I go through kind of this first row in my multiplication, I've got, let's see, I've got 1 times 0 plus 4 times 1 plus 7 times 0. This 1 here picks up the 4 from that first column, and I just get the 4. And then as you go through and fill in the rest of these columns, you're going to pick up the 5 and the 6, but everything else is just zeroed out. And then when you multiply and find the second row, this one here is basically going to pick up the entries in the first row of A, and as everything else gets zeroed out. So you get 1, 2, 3. And then finally, to finish out this third row, this one here is going to pick up all the entries in this third row from A and zero out everything else. So 7, 8, 0. So notice how I got this permutation matrix. It looks a lot like the identity matrix, but I just switched the first two rows. And what effect did that have on my matrix A when I multiplied by A? Well, when I did P times A, I also switched my first two rows. All right, so that's what these permutation matrices do. Whichever the easy way to think of it is start with your identity matrix and think about which two rows you want to switch, and make that switch, and you'll end up with the exact same result in matrix A. All right, so without even doing any multiplication work, just by looking, I can tell you that if I do, let's say, 1, 0, 0, 0, 0, 1, 0, 1, 0 for my permutation matrix, without even doing any matrix multiplication, I can just kind of tell you by looking at this that how this permutation matrix compares to my identity matrix is this basically the same thing, just with the second and third rows switched. So when I multiply A on the left by this permutation matrix, it's also going to do the exact same thing to my matrix A. It's going to switch my second and third rows. All right, so P times A, and you can double check this if you're not confident in this result, but P times A will be 1, 2, 3, 7, 8, 0, 4, 5, 6. So what you've been reading about in this section and doing partial pivoting, this idea of switching rows can be accomplished by matrix multiplication, multiplying everything on the left by this matrix P that does the row switches for you, or the pivoting for you. And what they're mentioning here in this theorem is if you can write A as the product of L times U, where L is lower triangular and U is upper triangular, well, you can also write A as a product of some permutation matrix times L times U. And so this there's going to be some permutation matrix P that takes care of your pivoting for you. All right, so that's what theorem 721 is telling us, is that any non-singular matrix A, not only can it be factored as L times U, but it can be factored as P times L times U, where P is a permutation matrix. All right, so hopefully that helps you understand what's going on there at the end of your section. Again, as usual, if there's anything else in this section of reading that gave you any trouble, please let me know and I can explain it for you.